Welcome to the AB Calculus video for skill number 142. I can apply the chain rule to differentiate composite functions. Alright, and the trivia question for today's video is at the very top of the capital, there's this piece here, and the name of it, that is the trivia question. What is the name of it? It shares the same word with another mathematical term for an old school calculator. Alright, suppose we had the function x squared plus 7 quantity squared and we wanted to take the derivative of it. One thing we could do is we could distribute it all out. So we write it as a product, we use our distribution properties, write it as a single polynomial, and then we take the derivative of that using polynomial rules. And we get 4x to the third plus 28x. And that's not too bad with a power of 2. But what if we had a power of 99? It's a distribution nightmare. Even with Pascal's triangle, that would take forever to write out and find what is the value of it. So we need a shortcut. And that is what the the chain rule is. It is a shortcut to avoid distribution problems. In fact, it's a rule that allows us to take derivatives of all kinds of composite functions, even composites of composite functions. So the chain rule states that if we have a function which is composed of two other functions, we can find that derivative by taking the derivative of the outside function, the f function, and keeping g inside, and then we take the derivative of the inside function. If you wanted to use Leibniz notation, you could say if y was a function of u and u was a function of x, then the derivative of y would be the derivative of y with respect to u times the derivative of u with respect to x. And I don't really like Leibniz notation, but it connects to some concepts later on in the year that makes it a little bit easier to understand, so I've included it. I usually think about this in terms of this format. The derivative of the outside times the derivative of the inside. So returning to that problem where we had x squared plus 7 to the 99th, if we want to take the derivative of that, here I show you with Leibniz's notation, the outside was u to the 99th, so u to the 99th, and the inside was, in terms of x squared plus 7. So here's the derivative of the outside, so u to the 99th, we apply the power rule to, and we get 99u to the 98th, and then the derivative of the inside is 2x. And if we wanted to, we could simplify that out, but first it would be better to substitute in our u, because our u is in terms of x, so we can do that, and we get 99 times x squared plus 7 all to the 98th. Now that it's all in terms of x, maybe we want to simplify, and we would get 99 times 2 is 198x, x squared plus 7 to the 98th. But, like Mr. Benches has always said, avoid simplifying because you might make an arithmetic mistake. So if you don't have to simplify, do not. And in this case, you did not need to. On the AP test, very often you don't need to either. So there we go. The derivative of the outside times the derivative of the inside. So for the future problems, I'm not going to use Leibniz notation. I'm going to speak more in the terms of derivative of outside times derivative of inside. Here in example 2, we're taking the derivative of a trig function, and these are notoriously composite functions because oftentimes the value that you're taking the the trig function of is a function in itself. So the derivative of the outside, we know that the derivative of cosine is negative sine, so we write negative sine times our argument. And then the derivative of the inside, when we take the derivative of 3x to the 5th minus 8, we get 15x to the 4th. So there we go, and then I just move the inside to the front in a pseudo-simplifying fashion. That's our derivative. Now, typically in calculus, we're doing more than just taking derivatives. We're doing stuff with the derivatives. So I wanted to show a couple common example problems. The first being common application problems. Example 3 says, find the equation of the line tangent to, and they give us an equation at x equals 0. So since we have an equation, what we can do is we use that equation and we find the derivative of it. And the first thing I notice is that it is a product, and so I'm going to have to apply the product rule. And this is where a lot of our skills are going to start stacking on one another. Here's the derivative of the first times the second, plus the first times the derivative of the second. So if you wanted to write that in prime notation, you said f prime g plus f g prime. And we take the derivative of the first, which requires us to use the chain rule. So there's the outside, the derivative of the outside, times the derivative of the inside, and then we multiply that by g, and then we add f g prime. And unfortunately, g prime did not require any chain rule. We did that because we wanted to find the slope at x equals 0. So we have this long equation, which is our derivative, and there's no need to simplify this because if we just want to evaluate it at 0, we can plug 0 in for all of our x's. And I did that here. 2 times 0 times 6 times negative 1 times plus 4 squared times 0. And all of that simplifies out to negative 48. So we now know that at 0, the slope of our tangent line is negative 48. And we take those two pieces and we're able to find out what the y-coordinate is by plugging 0 into the original function. And now we have a point and a slope. And we can stick a point and a slope into the point-slope form of the equation. And right there, leave it as is, because that's a functional equation for a tangent line.
Well, when life gives you lemons.
All right, and in example 4, we're returning to particle problems about position, speed, and velocity. This one's pretty straightforward. It says find the speed of a particle at time 5 if its position in meters is found with s of t equals tangent of 3t squared minus 8t. And we know that position is related to speed because speed is the absolute value of velocity, and we know that velocity is the derivative of position. So if we want to find our velocity equation, we need to take the derivative of our original function. And so we take the derivative of the outside, so the derivative of tangent is secant squared. And then we take that whole thing and we multiply it by the derivative of our inside. And because we want to know the speed at time 5, we're going to plug 5 into our velocity equation and take the absolute value of that. So we stick 5 into the equation and we get 25 times 3 is 75 minus 40. 5 times 6 is 30 minus 8. And we get secant squared of 35 times 22. And we want to take the absolute value of that. So I evaluate 1 over cosine of 35, because the reciprocal of secant is cosine. And since we're squaring it, we're going to do that twice. And then that gets multiplied by 22. So all total of those three things evaluate to 26.939. We have to remember to keep our calculator in radians So our unit is radians. And the absolute value of that is 26.939 meters per second. So our particle is traveling at that speed. And in fact, you can see that our velocity was already positive, so you can tell that the particle is moving to the right at that speed. And very quickly, I wanted to show one last example, which was a composite of a composite. And so what we have is we have the outer being squared. So our outer being squared is going to take the first derivative. So we take the derivative of the outside, we get 2 times the inside raised to the first power if you wanted to. So that was the power rule, and then we need to multiply that all by the derivative of the inside. Well, the inside is in itself another composite function. So first we take the derivative of sine, which is cosine, times the inside, and then we take the derivative of the inside. So this is a 3-function composite function. Alright, thanks for watching the video. Hopefully at the end of this you're going to be able to use the chain rule in multiple settings and basically find the derivative of composite functions. And the trivia question was, what is the name of this top piece of the capital? And I said it shares a name with another term, a mathematical term for an ancient calculator, and that would be the abacus. And if you don't know what an abacus is, it's that weird thing with the beads on it. You've got these bars that come down, and you're like, here's a bead and a bead and a bead, like that. And you slide them along up and down the bars to do calculations. Thanks for watching.